Welcome to module 8. In this module we look at the basics of Karnaugh maps. Karnaugh maps are essentially truth tables, but it is a slightly more convenient way of writing the truth tables. So, they are similar to truth tables, but they lead to what are called graphical methods for Boolean expression simplification. So far we have used Boolean algebraic expressions directly, but Karnaugh map is a very interesting way of graphically or visually combining various terms together, and it will give you something which is with which you can minimize the Boolean expression. So, the way Karnaugh map works is, for each min term we are going to assign an entry or a cell in the table. So, we are going to build something called a Karnaugh map table, and for each min term we will assign one location in the table. And so, if you have 3 inputs, then you know that the truth table has 8 different combinations. So, the Karnaugh map for it will also have 8 different cells, and the cells contain the information of the function for the corresponding min term. So, if a corresponding min term turns on, and then the function will turn on. So, we will see how to capture this information in the Karnaugh map. So, Karnaugh map for one variable essentially looks like this. So, if I have only one input A, then A can take 2 combinations, either A can be 0 or A can be 1. I can write it in this row form. So, A can be 0. So, corresponding to this you will put the entry m naught, and corresponding to when A equal to 1 you will put the entry m1. So, you can either do this or you can write the Karnaugh map like this. So, for row, so m naught corresponds to row 0 and m1 corresponds to row 1, and this part captures whether A is 1 or 0. So, when A is 1 you go and look at what is the value for m1. Similarly, in this one when A is 1, the value of m1 tells you what the value of the function is. If you want a 2 variable K map, we have f of a comma b. So, in this case A, the possible values of A are listed in the rows and possible values of B are listed in the columns. Right. So, in this case we go in the order 0 1, similarly 0 1 here. So, 0 0 corresponds to min term 0, 0 1 corresponds to min term 1, 1 and 0 corresponds to min term 2, and 1 and 1 corresponds to min term 3. If your function is AB, you can also use the combinations of A in the columns and combinations of B in the rows. So, in this case A is listed along the columns. So, as you move from one column to the other, A takes different values. So, in this column A is supposed to be 0, in this column A is supposed to be 1, in this row B is supposed to be 0, and in this row B is supposed to be 1. So, if you notice the min terms here versus the min terms here, they are only shuffled slightly. So, m00 and m11 are in the same place, 01 and 10 have moved to a different locations because A and B are swapped in the directions. And a 3 variable K map is let us say is a function of A, B, C. So, we have taken one of these variables, namely A, and we list all the possible values that A can take, namely 0 and 1, and for each row you list all the possible values that B and C can take. So, B, C can take 0 0, 0 1, 1 0 or 1 1, but as I said earlier, we will in the previous module I mentioned this, we will instead of having 0 0 0 1, 1 0 and 1 1, we will keep it as 0 0 0 1, 1 1 and 1 0. We will see why this is so in a little while, and the corresponding min terms are here. If you notice, this row corresponds to A equals 1. So, these 4 min terms m100, m101, m111 and m110, you can see that we are looking at A in the uncomplemented version in each of these 4 terms, and B and C are coming in all possible combinations. Right. So, this row corresponds to A equals 1 and this row corresponds to A equals 0. If you go and look at these 4 entries here, so you go and read it m011, 010, 111 and 110. If you notice, the second bit is turned on, right, which means for B equals 1, these are the 4 min terms that capture the fact that B is 1 or it is going to be in the uncomplemented form. And similarly, if you take these 4, this captures the information that C should be 1 or C is in the uncomplemented form. You can see that 001, 101, 011 and 111 has the last bit C, which is 1. So, this is a 3 variable K map. You can, so here I have chosen A to be along the rows here and B and C along the columns. You can also do a slight different rearrangement. In this case, C is picked to be along the rows and combinations of A, B are along the columns. So correspondingly the min terms will also get shuffled. So 0 0 with 0 gets 0 0 0, 0 1 with 0 gets 0 1 0 and so on. So you should not read from rows going into columns, you should read from columns going into rows, because we have fixed the order to be A comma B comma C. So we should read the bits for A first, then B, then for C. So this cell is corresponding to A equals 1, B equals 1 and C equals 0 or M6. And 4 variable K-map is essentially list all the combinations of 2 inputs along the rows and another 2 inputs along the columns, and the only difference is you see 0 0 0 1, a 1 1 and a 1 0 as we did in the previous example. Right. So in the 3 input case we had 0 0 0 1, 1 1 and 1 0, we will list them in the same order here 0 0 0 1, 1 1 and 1 0. The same thing for C and D, which are the 2 other inputs 0 0 0 1, 1 1 and 1 0. So in this table the last 2 rows correspond to the fact that A should be 1, or it corresponds to A being uncomplemented. The middle 2 rows correspond to the fact that B is uncomplemented. The last 2 columns correspond to the fact that C should be uncomplemented, and these 2 columns for D to be uncomplemented. So this picture here is essentially just picking CD for the rows and AB for the columns. So you can see that if I pick this cell, the function says it is in the order ABCD. So to say what min term should go here, I should look at AB here, which is 0 1, and CD here is 0 1. So this is M 0 1 0 1. If I look at this cell here, this corresponds to A equals 1 1 and AB equals 1 1 and CD equals 0 1. So this is M 1 1 0 1. So that is what we have here. So these 2 tables are actually equivalent, only that the order in which A, B, C and D are picked are different here. Let us see why the whole thing is useful. So all this thing that I showed so far does not really help you in doing anything better. So it is only just the table rewritten in a different form. However, let us see how we can actually use K-maps to simplify things. So let us start with this one, F is A plus BC plus D bar. Let us see how this thing can be represented in a table. So remember, this function is having 4 variables, namely A, B, C and D, and if I do not mention explicitly, we will keep the order always in increasing alphabetical order, A, B, C, D, X, Y, Z and so on. In this case we will assume that the function is written as A, B, C, D. I am going to take A, B along the rows and C, D along the columns. So you have A, B the 4 possible values, C, D with the 4 possible values, with this little twist. We go 0 0 0 1, 1 1 and 1 0, similarly 0 0 0 1, 1 1 and 1 0 here. Now let us see these 3 terms. So like we did with the truth table in previous module, I am going to go and fill up this K-map table with 1s and 0s. So the first term is A, right. So if A is 1, no matter what B, C and D are, F will become 1, and to capture that, right, so this is a place where A is 1. You can see that AB, you put 1 1 here and 1 0 here. So this corresponds to A equals 1, because that is a row where A is 1, and so are all these entries. If I look at all the entries here, they all correspond to A being 1. So B is of course taking 1 or 0, we do not care about that. So if A is 1, all these terms, right, correspond to the min term where A is 1. So all these are the min terms where A is 1. Finally, then let us look at BC. Let us find out all the min terms which correspond to B equal to 1 and C equal to 1, right. So if you go and look at this column here, so B is 1 and C is 1. So this is a min term which corresponds to B equal to 1 and C equal to 1, but that is not the only place. All these 4 cells correspond to B equal to 1 and C equal to 1. So you go and look at this. This is a row in which so these are the rows in which B is 1, these are the columns in which C is 1. So the intersection of that is these 4 cells. So these 4 cells correspond to the fact that B and C are both 1. Finally, let us look at D bar. So if D is 0, F should be 1, So wherever D is 0, we are going to mark, so we need a 1 there. So let us see, so if I look at this column here, we know that it's CD, where C corresponds to 0 and D corresponds to 0. So this must have a D bar, and so will this and this entry, because all of that corresponds to D being 0. Similarly, if I go and look at the last column, this also corresponds to D equal to 0. So this corresponds to C equal to 1 and D equal to 0. We do not care about the value of C when we look at this term here. So all those entries also become, they are all corresponding to the fact that D should be 0. Now wherever you see something like this, so this is true when A is true, this is true when either A is true or BC is true, this is true only when BC is true, this is true only when D is 0, and so on. So wherever you have some entry, you make all of them once, because that is what the truth table tells us. You can see that, right. So in this, for example, in this cell, A is 0, so this is 0, B and C are both 0, so this term is also 0. However, if D is 0, this cell should get a 1. So this is having only the information that D bar should be 1 for this cell to become 1, and in this specific case D bar is actually 1. So wherever we have some entry, we make all of them once. We do not need the sum terms we do not need the product terms anymore, we can drop it. All the terms that are not there, they become zeros. So these three entries are zeros. So if I go and write the truth table for this function, it will have 2 power 4 or 16 rows. Among the 16 rows, 13 rows will have a 1, and the rows corresponding to these 3 min terms will have a 0. You try it out. So I put it in the K-maps table, you go and put it in a regular truth table where you have 16 different rows with 4 combinations, and you will notice that min term 1, min term 3 and min term 5 will be zeros if you expand this function. Alright. So you go and try that out yourself. So let us see how K-map is drawn. We start with, so in this example AB and CD are switched around, the same function, but AB and CD are switched around. So first A is true for these 2 columns, then BC is true for these 4 cells, and D bar is true for these 2 rows. And we can do the same thing that we did before, wherever you have an entry you put a 1, and wherever there are no entries you put a 0. This is also a valid K-map. So this is essentially a different way of holding the same truth table. So far what we have is, the truth tables and K-maps are not different things, they capture the same functionality, except that the truth table will have a single vector for the column. So you will have one output vector, which is the last column. However, in a K-map, the ones and zeros are actually embedded inside either a square or a rectangle or something like this. So in this case, we have to pick the ordering of the inputs, and based on that we put the min terms correspondingly. Let us look at another example here, WZ bar plus XY bar plus X bar. Let us say that is the thing that we want to capture. So now let us go and see where WZ bar, what are the cells that correspond to WZ bar. We want W to be on and Z to be off, which means we have to look at the rows where W is on. So which are the rows where W is on? These are the 2 rows where W is on, but we also want Z to be 0 or Z to be off. So these are the 2 columns where Z is off. So the WZ bar will correspond to the intersection of the condition where W is on, which are these 2 rows, and Z is off, which are this column and the last column. So those are the 4 terms that correspond to WZ bar. Now let us look at the middle term XY bar. For XY bar, we want X to be on and Y bar to be on, or X to be on and Y to be off. Where is X on? X is on in these 2 rows in the middle, right. So and we take the intersection with wherever Y is off, that is this column and this column. So the intersection of these 2 rows and these 2 columns give me these 4 cells, these cells here, that is my XY bar. Finally X bar is these 2 rows. So wherever you have any such term, right, you started with a blank one, wherever you have such a term you put once, and you can get rid of the actual terms that gave you that, and wherever you do not have them you can put zeros. Okay. So, in the previous slide these blank cells must get a 0. Now, let us look at some important properties of K maps. So, one crucial property and the reason why we rearrange the whole thing is because the adjacent terms in the min term differ exactly by 1 bit position. So, if you go and look at any two cells which are adjacent to each other, so you go and look at this cell and this cell, this cell corresponds to wxyz being 0 0 0 1, this cell corresponds to wxyz being 0 1 0 1. So, if I take these two positions 0 0 0 1 and 0 1 0 1, it differs only in the value of x, w, y and z are all the same. If I take let us say these two cells, right, this corresponds to the min term M1001 or M9, and this corresponds to the term 1011 or M11. So, M9 and M11, if you go and think about it, they differ in exactly 1 bit position, namely the third bit. So, y is the only term that differs from this bit to this bit. In this place y is 0, in this column y is 1. Now, if I go and look at this table here, this is wxyz is given as a sigma of 0, 2, 3, 4 up to 11. Let us see how this can be filled up. So, this is a canonical sum of product. If you want to fill it up, this is 0, 1, 2, 3, right. So, 0, 2, 3 and they are on. Then the next row is for 4, 5, 6 and 7, right. So, among 4, 5, 6, 7 only 4 and 6 are on. So, let us do this once more. 4, we can see that 4 is here, so we put a 1, 5 is this term, but 5 is missing, 6 is the last column and then 7 you come back. So, you go from left to right, then skip, then come back, right. So, let us do it for this row. So, this is for 1000, that is 8, 9, skip, come back. So, 8, 9, 10 and 11, and this row would be 12, 13, 14 and 15. We can see that none of 12, 13, 14, 15 are there. So, all those cells are 0, and among 8, 9, 10, 11 we see 8, 10 and 11. So, 8, 10, 11 or 1, 9 is 0 and so on. One thing you can notice is even among the rows we have 0, 0, 0, 1, 1, 1 and 1, 0. The reason why we have this is because we want the same thing. We want the same thing, that the adjacent cells should differ exactly in 1 bit position. If I go and look at this cell and this cell, only w is changing, x, y and z retain the same values. So, this whole thing is interesting because we can then do what is called combining. So, these two cells differ in exactly 1 position, so are these two cells and so on. So, the other interesting thing is this cell and this cell also differs only by 1 position, even though technically they are not adjacent to each other in the picture. What you can see is this term is corresponding to 0, 0, 0, 0, this corresponds to the term 0, 0, 1, 0. So, the leftmost cell and the rightmost cell here are actually adjacent of each other because they differ in only 1 bit position. So, one way to think about this is you take a paper like this, right. If you put up entries here, right. So, you know the adjacency right away. If you write it in the order 0, 0, 0, 1, 1, 1, 1, 0 and so on, you know what adjacency is. What else is adjacent is if you are able to roll the paper like this, right. So, what I did is I had a table like this. If I roll a paper like this, whatever cells are adjacent we call them adjacent also, or I have a table like this and I roll a paper like this, right, one row folding into another, whatever cells are adjacent, they are adjacent in K map sense. So, what we have is this row is adjacent to this row and this column is adjacent to this column, right, and otherwise graphically whatever is adjacent is also adjacent. So, this is an interesting property of K map. This is possible only if you write it in this order 0, 0, 0, 1, 1, 1 and 1, 0, not if you write it as 0, 0, 0, 1, 1, 0 and 1, 1. So, these are showing other things which are adjacent of each other. So, the purple one and the green ones are also showing adjacencies. So, the reason why this is interesting is if you take two min terms that are adjacent and if you combine them, the product term simplifies by one less variable. So, I will explain what that means. So, let us take adjacent terms now, let us take this column, right, let us take this column. Graphically we can see that these are adjacent to each other, right, this is adjacent to this. Now, let us go and write the expression corresponding to this. What is the expression for this? This is A bar, B bar, C bar, and the expression corresponding to this min term is A, B bar, C bar. So, these are product terms. The expression which captures these two ones is A bar, B bar, C bar plus A, B bar, C bar. You can see that B bar, C bar is common. So, it is A bar plus A, which is same as B bar, C bar. If I take two ones that are adjacent to each other and if I combine them, it knocks out one of the variables. In this case, we know that BC is constant, we are not changing the values of BC, we are still in the same column, but we are going across multiple rows. Whatever rows we are going across, we can eliminate them. So, if you do the same thing here, for instance, right. So, this will correspond, this term will correspond to A bar, B, C bar, this one will correspond to A, B, C bar. If you combine them, it is B, C bar. So, if you combine these two, you can just look at, oh, I have combined these two, I do not have to look at A at all, what is the term corresponding to this one? So, it says B should be 1 and C should be off. So, this last column corresponds to B, C bar. Let us do this one more time. Let us look at this two ones which are adjacent to each other. If I group them together, this term corresponds to A bar, B, C, and this term corresponds to A bar, B, C bar. So, we have that as an expression here. A bar B is common, so A bar B you can take it out, and these two ones correspond to A bar B. So, from the picture, if I want to infer that, I can say that the oval is across these two ones. In these two ones, if you notice where the columns are, the column for C is changing, the column for B is remaining the same at 1. So, B is remaining at 1, and this is in the row 0, we have not moved to row 1. So, row 0 for which corresponds to A bar, we have A bar. So, this is corresponding to A bar B. So, the way I read this is I looked at which columns it is crossing, and that variable will not appear in the product term. Wherever you see the labels are constant. So, in this case the label for B is constant, it is for 1 and 1. So, B is constant across these two columns. So, I put B here, and it is in this row where A is corresponding to 0. So, I take the logical AND of those two. So, it is A bar and B. So, you can as an exercise try and see what is the expression corresponding to grouping this min term and this min term, right. This min term and this min term, if you group it together, they are adjacent because I talked about this, right. You can fold, and if the paper will touch each other, so you can take the table and fold it, and the one here will touch the one here, right. So, you go and find out what is the term corresponding to taking these two ones and combining them, and you will see that it is actually corresponding to the fact that A should be 1 and C should be 0. So, you will see that the term corresponding to this is AC bar. So, I do not need to do Boolean minimization like this, I can straight away tell you that the ones that are here and here will combine and give you AC bar, and the ones that are here and here will combine and give you A bar, C bar, right, because it is A bar and this corresponds to C bar. You can try and verify that yourself. So, this brings me to the end of this module. So, what we saw in this module was we were able to take Boolean expressions and we were able to write it in terms of K maps. We will see how this K map is graphically, even though it is in some sense similar to the truth tables being rearranged, it gives you something really powerful, that the adjacent rows and adjacent columns, if you combine them, they are going to knock out one variable and so on. We will use this fact in a lot more detail in the next module. So, as of now, just try these little exercises and try and figure out the terms by doing the Boolean expression yourself and minimizing, as well as just by looking at the labels of the rows and columns and guessing what the entry must be directly. So, try and do this yourself. Thank you.